What if everything we thought we knew about the fabric of reality was just the surface of something far more profound? The James Webb Space Telescope has captured something that shouldn't be possible: anomalies in deep space that Google's quantum computing team suggests could be evidence of dimensions beyond our own. In a series of images taken of the distant AEL 2744 galaxy cluster, Webb's infrared cameras detected strange light diffraction patterns that defy conventional physics. Models. These aren't just any anomalies. They're precisely the kind of quantum signatures that theoretical physicists have speculated might appear if higher dimensions were interacting with our observable universe. Google's quantum AI researchers, using their advanced quantum algorithms, analyzed these Webb telescope images and found mathematical patterns that align remarkably with string theory predictions of how extra dimensions might manifest. The team published their preliminary findings last month, sending shockwaves through the physics community. What if everything we know about physics is about to change? What if the three dimensions we experience are just a fraction of what actually exists? The implications could rewrite our understanding of reality itself. The paper just published by Google's quantum AI research team has generated intense interest within the scientific community. For the first time, researchers are using quantum computing algorithms to analyze James Webb Telescope data in ways never before possible, specifically focusing on unusual radiation patterns in these deep space images. What makes this research so groundbreaking is that the team isn't just examining pictures, they're extracting mathematical signatures buried within the cosmic background radiation. According to their preliminary analysis, these signatures appear to align with theoretical models that predict how higher dimensions might interact with our universe. The lead quantum researchers on the project are examining these findings with rigorous scrutiny. What they are observing are pattern anomalies that warrant deeper investigation, mathematical consistencies that their quantum algorithms detected and that traditional computing analysis might have missed entirely. The researchers are carefully studying a specific set of Webb images from the AEL 2744 region, where unusual light diffraction patterns do not align with what standard physics would predict. This discrepancy is exactly what some theoretical physicists have long suggested might appear if higher dimensions were influencing our three-dimensional reality. The James Webb Space Telescope represents humanity's most advanced window into the cosmos. Unlike its predecessor Hubble, Webb's infrared capabilities allow it to peer through cosmic dust clouds and capture unprecedented high-resolution images of the most distant galaxy clusters ever observed. When pointed at the AEL 2744 cluster, nicknamed Pandora's cluster, Webb captured images with a level of clarity that astronomers had only dreamed of. But it wasn't the astronomers who first noticed something unusual in these images. It was Google's quantum computing team. The quantum team processed the Webb images through their advanced quantum algorithms, specifically designed to detect patterns invisible to conventional analysis. What they found was astonishing: unusual light diffraction patterns around certain galaxies that do not conform to standard physics models. These anomalies appear as subtle quantum-level distortions in the infrared spectrum. When mapped against expected light behavior based on our current understanding of physics, there are discrepancies that cannot be easily explained. What the quantum team discovered next challenges everything we thought we knew about the fabric of our universe. When they expanded their analysis to multiple galaxy clusters, they found the same pattern repeating: a mathematical signature that aligns perfectly with theoretical models of extra-dimensional space. This is why some leading physicists are saying this could be the biggest discovery since Einstein's theory of relativity, potentially rewriting our fundamental understanding of reality. Leading physicists are now developing testing protocols to verify whether these are truly signatures of an extra dimension, rather than the result of instrument error or a natural phenomenon. They are designing new observations that could definitively confirm or refute these findings. What's at stake is nothing less than our entire understanding of physics. If confirmed, this discovery would validate decades of string theory research and help explain long-standing mysteries such as dark matter and dark energy. It would imply that what we perceive as our universe is just one layer of a far more complex reality, with profound implications for everything from quantum mechanics to gravity itself. To understand why these findings are so revolutionary, we must consider string theory, one of the most ambitious frameworks in modern physics. Unlike traditional physics, which treats particles as tiny points, string theory proposes that they are actually tiny vibrating strings, too small to detect with current technology. For string theory mathematics to work, our universe needs more than the 3 spatial dimensions we can see. It needs at least 10 dimensions, 6 of which would be curled up so tightly they are normally invisible to us. These hidden dimensions could explain why gravity is so much weaker than other fundamental forces. Harvard physicist Dr. Lisa Randall has pioneered some of the most compelling models for how these extra dimensions might be detectable. Her groundbreaking work proposes that some of these extra dimensions might not be curled up as tightly as others, potentially allowing them to have measurable effects on our observable universe. One of Dr. Randall's key insights is that gravity, unlike other forces, might leak into these extra dimensions, creating subtle distortions in how light travels across vast cosmic distances. These are precisely the kinds of anomalies the key Webb telescope might now be capable of detecting. This is where quantum computing becomes essential. Traditional computers process information in binary, yes or no, 1 or 0, but quantum computers use qubits, which can exist in multiple states simultaneously. This allows them to analyze complex patterns across multiple mathematical dimensions. The quantum algorithms used by Google's team are specifically designed to detect extremely subtle correlations in data that would appear as random noise to conventional computers. These algorithms can, in effect, think in higher dimensions, making them uniquely suited to spotting patterns that might indicate extra-dimensional effects. If these findings hold up, what would an extra dimension mean for our understanding of the universe? Imagine a flat sheet of paper as a 2-dimensional universe. Beings living on that paper could move only forward, backward, left, and right. But we, in 3 dimensions, could touch any point on that paper by moving through the 3rd dimension. Similarly, an extra dimension would mean there's another direction, one we can't see or move in, that could manipulate or affect the fabric of our universe. What's truly remarkable is how these quantum algorithms are revealing patterns that traditional supercomputers entirely missed. For decades, we've been looking at the same cosmic data through conventional computing lenses and seeing nothing unusual. Now, with quantum analysis techniques, we are spotting mathematical signatures that have been hiding in plain sight all along. Could we be on the verge of the biggest paradigm shift in physics since Einstein? What other cosmic secrets might we uncover using these tools? If these patterns truly represent evidence of extra dimensions, the implications would be staggering across multiple scientific fields. In physics, it would resolve one of the greatest puzzles of modern science, the incompatibility between quantum mechanics and general relativity. Extra dimensions could explain why gravity is so much weaker than other fundamental forces. In cosmology, the detection of extra dimensions might finally solve the mysteries of dark matter and dark energy. What we currently attribute to invisible matter and unknown energy could actually be gravity interacting with these hidden dimensions. This would explain why, despite making up about 95% of our universe's mass energy, we've never directly observed dark matter or dark energy. Research. Teams at institutions like MIT, Caltech, and Princeton are already designing follow-up studies to test these findings. They're developing new methods to analyze Webb telescope data and creating simulations that predict how light would behave if it were interacting with extra dimensions. Several teams are requesting additional observation time with Webb, focused specifically on the anomalous regions. The skeptical perspective remains essential in science, and alternative explanations are being considered. These patterns could be the result of previously unknown quantum effects that don't require extra dimensions. They might be artifacts from the telescope's instruments or data processing methods, or they could represent a completely new phenomenon that still fits within our current understanding of physics. Detecting extra dimensions has always been considered extremely difficult because they are likely to be extremely small, with exceedingly subtle effects. The physics community has emphasized that extraordinary claims require extraordinary evidence, and finding an extra dimension would be among the most extraordinary claims in the history of science.